So let's go ahead. I'm just looking how I can get this image away here. So not yet perfect. Okay. In the last week, we have talked about testing and how to get data on failure rates, on lifetime. And I think just having data on failure rates is not sufficient, but we also must know why it fails. So that's the reason why in end-of-life testing we test so long until we get failures, and then we can analyze these failures. And failure analysis leads to kind of modeling which is called physics of failure, and that is both quantitative and a qualitative modeling of failures. Here I would like to explain what the methods are which can be used, and we can say there are mainly two fields. One is analysis, which can already be done on new samples, also some non-destructive testing, and on the other hand we have really dedicated analysis methods. For instance, when we want to know bigger defects, we can look at pores or delamination. We could say delamination can be a result of a failure process. Pores are often the cause of some failure process. And here we have analysis methods like X-ray transmission, mainly for the porosity, and delamination, which can be analyzed, for instance, with ultrasonic microscope. Then often we want to look at the topography of fracture. So that means the fractured surface. Can we see whether it's a ductile fracture, whether it's a fatigue or a brittle fracture? And the best tool for let's say 50 to 60 years now is the scanning electron microscopes. I must say, in the IMTech, many laboratories have a scanning SEM of their own, and a new advancement is here a focused ion beam, where we can even do some cutting in the scanning electron microscope. The chemical composition is often detected inside the SEM, and here we have additional methods like electron spectroscopy and electron excited spectroscopy of X-rays is the correct terminology. We can have secondary ions, or we can have Auger electrons, and all of these give information on the elements that are present and on their chemical binding state, which is also very important. Also, in my lab, for instance, we have many possibilities for stress analysis. So that can be done with X-ray diffraction, with X-ray reflectometry, with optical topology, metrology, and also using special test chips. Okay, now that is just to show you how many defects we can have and what can fail, like the interconnects, the die attachment, package defects, leakage, hermeticity. The leads on the outside can fracture, we can have corrosion, and we have the chip metallization, we have high aspect ratio structures which are very sensitive against vibration and shock. We have cracks in the silicon, and we have, of course, shift of electrical parameters. And here we have all of these methods which must be combined in a very intelligent way. For some it is easy. For instance, the interconnections like the wire bonds can be analyzed with almost any of these analysis methods, while on the other hand, high aspect ratio structures, they mainly must be analyzed in a SEM. Okay, so now let's imagine we have done the testing, and after the testing we must look for the defect. First of all, we must localize the defect, and the second is we must address the proper position where the defect is. And again, here there are quite a number of layers which must be taken into account. Imagine, for instance, we have a car. The car breaks down because some electronic control unit is no longer functional. So here we can see these are, here is a printed wiring board, here is a ceramic circuit, here is some mechanical structure. Inside we have some integrated circuits, and the defect can be on the surface of such integrated circuit. So there are quite a number of strategies how to find the defects. In most cases, or in many cases, in systems from the field, the device is dead, so we can have no longer electrical measurements. In some cases where the device just shows faults, so that means it is defective somehow, but it is still working, we can have different methods. For instance, we can use thermography, and sometimes we can find some hotspots. Yeah? A hotspot is a location where we typically have a increased power dissipation, and that power dissipation leads to heating, and that heating can be seen sometimes, but that's a rare condition. So analyzing failures is a little like work of Sherlock Holmes, and it's quite complex, and in order to find out the real reason, it is requiring lots of experience. Okay, so let's proceed how it would work. For instance, we have a chip which has a hotspot, and that hotspot sometimes can be seen through the molding compound with so-called lock-in thermography. In that method, the device is heated and cooled with a certain relatively low frequency, and in that way, by lock-in technique, a hotspot can be visible, which would hardly be seen otherwise, because it's maybe only a Kelvin or so hotter here. When we know where that defect is, we can address the location. One of the possibilities is just to open the package. So that is often done using first some mechanical method, but we cannot go down to the chip. And in a second step, we have some laser ablation, which takes away the molding compound, and that must be done in a way which will not damage, for instance, wire bonds. This can work, and after the laser debonding of the molding compound, we can go into the focused ion beam. A focused ion beam is a small probe of a high energy ion beam which has a diameter of, let's say, 10 nanometers. And with that beam, we can cut through very small features here, like this bonding wire. So we can see here already the internal structure. That is a wire bond which has been cut through the length. And when we address such a wire bond here, which was on the chip, we can see here there are cracks. We can see the crystal structure under the bond, and that crystal structure can be a result of some brittle phase. For instance, here it was analyzed that this phase is something like aluminum 3, gold 8. That's an intermetallic phase, which is brittle, and here this will create a crack. So first localization, then we have the target preparation, then we have the failure analysis itself. This here is a so-called EBSD image, and that means electron. No, I must get the pen. That means electron backscattered diffraction, and here we can see the crystal orientation. So we see there is a so-called texture inside that wire, and that texture is modified, for instance, by the melting of the ball. And in that case, we can see it is a very good wire. The heat-affected zone here has no modification against the regions which are away from the ball, so that probably will be a strong wire. And in that case here, the necking area was not the problem, but the interface here. Okay, now we can say we have this focused ion beam, and I would like to go into more detail. So after laser or plasma opening, we have a metallographic section that can be, or when we want to have a very fine cutting, we use this ion beam. Typically that's a gallium ion that has a high mass, and due to that high mass, we can see that the ablation rate is very high. But on the other hand, the ablation rate is so low that for ablating, let's say, cubic millimeters, you would use thousands of hours just to bring away that material. So it's important first to have such plasma or laser processes. Here we see, for instance, a wire bond in which very strong intermetallic phases have grown. These phases are not necessarily detrimental, but in that case we see no cracks, and there are intermetallic phases between gold and aluminum in every gold wire bond. On the other hand, what we often see near wire bonds is cracks. A crack going down like this is something like cratering. Here in that case, I would say that is a burning hole. So here in that location was overheating. We can see the silicon is molten and the complete structure is deleted, and in that case such a crack is just a secondary damage we can find here. Here, that's a classical metallographic section in a light microscope. What we can also see that is slightly blurred, and the reason is that in the, let's say, quarter to half micrometer range, the resolution limit of light microscopy is reached. So, scanning electron microscopy is very good, and at high magnifications combined with a focused ion beam where we can just cut out a slice, for instance, is very helpful to go into the details here. Other, let's say, some kind of tricks are using, for instance, different kind of light. Here, that was a printed wiring board. Here we can see the glass fibers inside the epoxy. We can see this internal structure of the copper leads. So that was electroplated. So we from the bottom side here up, and in that way, from that side here to up, and here is this structure coming up of the single crystals. The UV light leads to fluorescence of some of the features, for instance, here in that case of the glass fibers. So using the appropriate illumination is also very important. This here is a focused ion beam. We can see it's mainly a scanning electron microscope. That is the SEM column, which creates a nanometer thin beam of electrons, which are targeted at the sample. On the other hand, here is a focused ion beam column. That's more or less the same like a SEM column, just that it doesn't use electrons, but it uses gallium ions. So these are targeted here on the specimen. Here is the chamber. And what we also have is some detector on the backside, which is for X-ray spectroscopy. Again, here we can see the damage in a multi-layer metallization structure of an IC. That whole device was developed by one of my PhD students roughly 10 years ago, and his main task was to add a laser to the focused ion beam. So with the laser, we have 1 cubic millimeter of material which is removed within 17 minutes. On the other hand, using just the FIP to remove such amount would take 1.1 years. So let's say 12,000 hours or so. On the other hand, state of the art in FIP has changed in the meantime, so they have also become significantly faster, but still this combination is very important, and the Zeiss company is now selling this model here. Okay, again, here is such a FIP section. Here we can see that is a flip chip interconnection which was damaged. We can see it's a typical fatigue damage. It is just a very a structure which is broken up completely with many cracks and pores, and that is due to thermal mechanical deformation. So first, this is cut with the focused ion beam. Then we target a primary electron beam onto the sample. And what is the most important information is secondary electrons. Secondary electrons give a good image. And that is a topography contrast. So here we really see the structure in a more or less 3D way. When we want to see more the material contrast, so that is used with backscattered electrons. The secondary electrons have a very low energy. They come out like a, let's say, like a cloud. The backscattered, they really come back with a high energy. So we need other detectors, and that's the classical way. Another thing is when you target electrons of, let's say, 0 to 30 kiloelectron volts, at a material, you will get X-ray. You get characteristic X-ray lines, and these can be used with EDS or EDX. And using EDX, we can see which materials are inside. The resolution is not so high, so we can get maybe a maximum of 1%. If it's lower than 1% of content of an element, we can hardly see it. But on the other hand, that's still important. We can also make an image with the absorbed electrons. And in an Auger spectroscopy, we have very low energy electrons which give information on the chemical binding in very thin layers. So in that way, we can analyze layers which are very thin and volumes which are very, very small. We must say, typically we will not get to lower volumes than maybe a cubic micrometer or so. That's a typical thing for EDX analysis. Okay, here is another example. In that case, it was another PhD student, and here we could find when we have high cycling with very high temperature amplitudes, let's say almost 300 degrees centigrade, we have a very low number of cycles which can be tolerated here. On the other hand, what we did, we developed different metallizations. So that black is the initial we developed multilayers, and using multilayers we can increase the number of cycles significantly. That was a dependency between the material behavior. So the higher the strength of the material, the longer the lifetime is. But on the other hand, we also wanted to know what happens here. And the result is that due to a deformation of the aluminum, which leads to extrusion and to a certain pressure under the passivation, this passivation at some time cracks. So that crack of the passivation leads to the fact that aluminum comes out, and in the end it leads to a short circuit. So that's not a fatigue phenomenon, it's more like blowing up an air balloon, and when you put too much pressure on it, it will just break. So in fact, Using this information we got from the failure analysis, we could improve the system. The two things was increase the strength of the passivation and also make the aluminum undeformable just by making it as a multi-layer. So in that way, the lifetime could be increased significantly. Again, here another example of that dissertation of Mr. Martens. It was his demonstrations. Here you again can see that is a stacked package, which was very popular at that time in order to have some hybrid integration, and the connections were made with a very small flip chip. And again, here we can see there is a strong degradation of the flip chip. Also, the quality of the flip chip, especially the alignment accuracy, is not very high. Okay, but now let's come back to the more simple things. Here we have an example just of a printed wiring board. Printed wiring board is typically coated with some varnish. So either we just have the solder resist alone, and in that case all of the metal contacts will still be open, because if you would coat them with solder resist, they would not be solderable. On the other hand, you must do a coating after the soldering, and of course that coating is costly. So you do either some lacquering or you put on some silicone potting, but in the end it costs money, and so people want to save it. And here that was a result of just a laboratory investigation. We tried out what happens in a 85-85 test after we have not coated this printed wiring board. And we had some very strange behavior. In that ECU board we had no failures, but we had faults. So suddenly it didn't work anymore. After some reset, it was operational again. And that was very strange, and because it didn't really fail, but it was faulty. So one of my colleagues, she took it into a microscope, and here we found these very small feather-like structures. Such structures are called dendrites. And in order to know what it is, we put it in a SEM, and here again we first thought there had been a spider or something. Is it a spider web? No, it is not. The EDX analysis was showing we have silicon. Okay, where's the silicon? That's clear, that's from the glass fibers. Here we have lead. That's from the solder. We have tin, that's also from the solder. Okay, but why do we find it here? And then we also find something which is very, very strange. We find some chlorine. And chlorine is the strongest corrosion promoter we can have here. And in the end, it was no clean solder paste, which was not clean enough. So we had ionic contamination. The contamination is less than 1 microgram per square centimeter of printed wiring board equivalent. So it's a very, very low content, but it can already lead to corrosion. That leads to the fact that on the anode here, so where we have an anodic voltage, tin lead at that time was dissolved. There was some humidity film on the surface because it was not coated, and the ions migrated and they were electrodeposited on the cathodic reduction. And so this small tree here was growing until we had a short circuit. And after that, there was a small flash of lightning. That tree was evaporated, and the whole game began from new. So, strange thing, this led us to the knowledge or to the know-how that it would not be possible to avoid such coating of the ECUs. And so, after many years, ECUs are still coated after the soldering in order to prevent the deposition or the precipitation of a very thin water film, which is deadly in combination with electrical potential and in combination with ionic contamination. So this just could be cleared up with using two very simple instruments, which is the light microscope, and that is the scanning electron microscope in combination with an EDX. So, okay, here we have some table which shows us the main information and the main characteristics of such analysis methods. So, still, let's say the bread and butter method is X-ray microanalysis in a SEM. Excitation is by electrons. We have characteristic X-ray radiation. The information comes from 0.5 micrometer to 5 micrometer penetration depth, and the lateral resolution is roughly 1 micrometer. So you could say the volume which where you have the excitation is maybe a cubic micrometer or so. You can detect all elements except the very light elements. You have a quantitative analysis, but maybe the accuracy is much worse than 0.1%. Okay. Using a similar system, you can have Auger electron analysis. Here you have a very high resolution of the energy of these Auger electrons. The lateral resolution is very low, only 35 nanometers. We have a depth of 1 to 5 nanometers, so you can analyze only few layers. Typically, you do a sputtering after an analysis, so you can get a depth profile. The detection limit is similar to the X-ray analysis. And here, that's a secondary ion beam microanalysis. We have only 1 nanometer and also a somewhat higher resolution, but the detection limit is in the part per billion range. So, in the IMTEC, we mainly have the X-ray microanalysis and the ion beam microanalysis. I don't think we have an Auger analysis here. Okay, these were the post-mortem analysis methods, but still we also would like to see some non-destructive testing. So non-destructive testing is very often applied in quality control, just to take some specimens before and after testing to see if there are defects. The main advantage is that after non-destructive testing, you still have the specimens alive, so you can go on testing with them. And here is 3 most important methods. One is visual inspection with microscope or with no microscope. Of course, it is quite limited. On the other hand, we have X-ray inspection. We all know good old Konrad Röntgen, who invented or he found the X-ray. And we have scanning acoustic microscope, and I will explain these a little. So it is important to know about these methods. So what we have first is X-ray radiography. So we have an electron beam which is targeted, at, for instance, a copper cathode, and yes, it's a cathode. It's cathode rays, and so we have the emission and mainly of X-rays, and these X-rays are a very wide spectrum, both characteristic and radiation from the complete spectrum. And just by ray tracing, we can find how the rays go through this specimen. Of course, when we have some sample here, we can see when there is much mass in between, we have an absorption. When there is less mass, there is less absorption in between, and in that way we can say if there is something in between, it gives a shadow, but that shadow is not a 0-1 shadow, but it's partly transparent, and the transparency depends on the thickness here. So in that way, just by a 2D method, we can do images. Here, these are 2D, and these here are 3D. 3D is also called tomography in German. Okay. Generally, it is a very good method of seeing inside, for instance, a package. What is the background? If an X-ray beam goes through some matter, the intensity which comes out depends on the intensity which goes in times e to the power of minus alpha, which is the absorption coefficient, times the thickness through which it goes, and through and some concentration of the material, where the concentration is measured in gram per cubic centimeter. So when several layers are penetrated, the intensity is reduced in a multiplicative way. So of course, always the initial intensity is important, and the individual thicknesses of the layers as well as their absorption coefficients are important. Absorption mainly depends on the Z number of the element here. So, and on the density. So high Z number means heavy elements, and also high density also means heavy elements. And these heavy elements have a higher absorption. So the highest absorption is in lead, it is in gold, also it's relatively high in copper and silver, but it's very low in polymers, because these only consist of carbon, hydrogen, oxygen, and sometimes a little silicon. Okay, just to give you some information on the absorption coefficient of carbon, it's extremely low. Of lead and tungsten, for instance, it's roughly 20 times higher here. What is important is the magnification. So we just have a ray tracing. We have a focus, but the focus is where the beam is emitted. So it's in fact the focus, not on the specimen, but it is the focus of the electron beam in in that cathode ray tube. And so if we say this focus length from focus to the sample, it is this length here, and if the detector is a little more away, the magnification is M is FDD divided by FOD. So FDD is the complete length here. And the FOD in that case is the length here. And in that way, it is important that we come here closer to the focus of the tube, and in that way, of course, the magnification can be increased significantly. Typically, now magnification is, it can be several hundred times, but what is more important is the resolution. And we can say now in modern X-ray analysis, the resolution is very similar to the best resolution in light microscopy. So that means the resolution is significantly below 1 micrometer. Here are some examples. For instance, that's a small IC device. What is tolerated here under the chip, we can see the silver epoxy material for the dye attachment, and there are pores in it. On the other hand, when we address this, we can see the pores here. That is still not dangerous because the porosity is below 20%. But here in that case, porosity is, let's say, 60 to 70%, and that leads to a high thermal resistance, and such device can die just by overheating at a certain power rating. Another thing which is important is X-ray tomography. In that way, we have an X-ray source. Of course, it should be a point source. The sample is moved, and we get images for each position of that movement. So there are several angles of rotation, and in that way, we get views under many angles. So it's like stereoscopic imaging, but not with 2 eyes, but with many eyes. And adding up all these informations, we can do a so-called radon transformation. That's a mathematical method to get from many 2D images a 3D image, as we can see here. That's an image where we have, again, a flip chip circuit. It's a small ball grid array, and also we can see inside here the via holes, and we can see the wire bonds. Unfortunately, taking such an image takes very long time. Just to give you an example, such an image, that's just a question of seconds, and when you can even do 100% production control with a rate of let's say 1 per second, or such high frequency. On the other hand, the frequency here would be maybe an hour or more per specimen. So 3D takes lots of efforts, and 3D is very expensive. So typically if you assume that such a machinery for tomography is expensive, maybe you pay 250 euro per hour, and that means such a 3D image will cost you 250 euro or more. Again, here are such images from different applications. Again, often just the relevant information can be taken from 2D images. In that case here, again, the 2D image was recalculated from the 3D image. Here is another example. We have the via holes. The via holes should be filled with solder. Unfortunately, some are not. When you have some, let's say, 2D X-ray here, you don't see anything. But when you take 3D, you can clearly see it. So that is, again, a method which is well suited for post-mortem analysis when something failed, but it is not so good for just quality control. Maybe it's good for quality control when you build a satellite for 200 million and shoot it into space. Then everything should be checked with tomography first. Now, the second method is scanning acoustic microscope. So it is important to note a scanning acoustic microscope is a method aiming at interfaces. The X-ray is a method aiming mainly at volumes, yeah? Because for absorption, you need a certain thickness of penetration, and in that way, you have volume effects of absorption, but in the scanning acoustic microscope, you have reflection. You have a high frequency. It can go to 1 gigahertz now. So that should say G. And that is a transducer which has something like a sapphire lens. And that sapphire lens concentrates the ultrasound to a certain focus. That is not a variable frequency you can have here, but for every frequency you use, you must have a different transducer, because that lens always has a certain focus length which depends on the frequency or on the wavelength of your ultrasound. So the ultrasound goes into the sample, and then you can either say it's either reflected or it's going through. So you can have ultrasonic investigation. You can have ultrasonic investigation in reflection, which is mostly done, or in transmission. But what is important, you have a reflected signal energy, and that reflected portion is depending on the acoustic impedance of the second material minus the acoustic impedance of the first material, where it comes from, divided by the acoustic impedance of both materials. In that way, you can say when, for instance, an ultrasound wave comes to a stiffer material and a material of higher density, it is reflected. So it's something like this in the room. The wall has a high acoustic impedance, significantly higher than the acoustic impedance of the air, and so you get a reflection of sound. And it's the same when you are just in a solid body. Okay, so you get a reflection. On the other hand, the reflection is from a certain depth, and that depth is, if it's one material, it's the speed of sound times the time you have from a ping until you hear again the reflection of the ping, of course divided by 2 because it goes back and forth. And in that way, you can have a reflection, and in A-scan, you can just have it point-wise, and then you get an image on your screen. So what you can say is you have your sample, and you move here, and in that, for instance, you move on your screen, and in some locations you just get a reflection, and in that way you see here we have a defect. Yeah? So here it would be defective. So that's the specimen, and here it's the screen. So it's very much same principle like a SEM. You have a probe on the specimen, and you have a probe on your screen, and the signal you get from a sensor gives you just a modulation of your screen brightness. And in that way, you mostly have a C-scan, C mode. That means you focus at a certain depth, and in that depth you look if there are defects or not, as I was showing you here. And that's a method where you can also get resolutions down to a micrometer when you have very high frequencies of ultrasound. So in typical applications it goes maybe to 100 megahertz, but special systems can go to 1 gigahertz. Okay, now I give you some examples. That was from very old investigation. That was the power device of a smart car. At that time we planned to build a electro vehicle called smart car, which was the smart car as you still know it, but we planned to build it as an electro vehicle. And during that investigation we had the semiconductors, and after some power cycling the semiconductors just fell off the substrate, and we wanted to know how the speed is, and so we had several cycles. For instance, here we had cycles up to 125 degrees centigrade, and then we could see that from the border of the interface, so that was just looking at the solder, we suddenly see that there are defects, and that these defects are growing a little. So it's still not so strong after 1,500 cycles, but still you can see an effect. The defects are growing. On the other hand, when you look at the base plate, so in that case it means that interconnection here, the problem was more severe. Here you can see in the base plate how in several layers we can have a delamination, and here in one case, for instance, having the wrong base plate, after 1,600 cycles we have almost no more attachment. If it's a material like this, aluminum silicon carbide, which has a CTE very similar like that of the semiconductors, in that case you can see the structure of the die attachment doesn't change at all, so that was reliable. Also we could find, when we were measuring the crack length here as a function of temperature cycles, we could see it was a big problem in copper, so it increased very fast for a copper base plate, and for just a normal steel base plate it was growing significantly slower. Okay, so it is important for assessment of reliability to do lots of additional investigations. Of course, the most important thing is always to maintain electrical properties. Sometimes you cannot get these properties, so you have some other property as a replacement. For instance, you can look for a crack length, or you could look for a strength. One of my PhD students, he has developed test equipment to measure the thermal resistance. So if in the testing suddenly the thermal resistance goes up, temperature will go up, and that is a good hint to show us there are cracks developing inside here. Of course, post-mortem, I have shown you all of the failure analysis, and what is also always necessary is to have several different tests of reliability, because only after these you can do the failure analysis. Okay, so I would like